All right, this seemed like a quick way to show you what's going on here. I've got a mystery mass hanging from these scales, and in the notes I'll have the angles for these scales. But if you look over here, you can see this one reads about 8. This one reads about 8. And then if you come over here, I've got another setup. Got a mystery mass hanging there. If we follow this string, please, Mr. Harding, clean your tables. It's about 13 newtons. And over here, that's about maybe 11 newtons on that side. Okay, so that's the lay of the land. All right, so what I have over in the notes then, this is an app on my phone that allows me to measure angles that I'm seeing with the camera. So I just set it up kind of across the tops of those posts because I knew that was level. I just wanted to show you then how this gives a reading when that's perfectly horizontal. That gives a reading of 0 degrees. So then when I went to the initial setup where the scales both read 8, can you get that to go away? Can you go away? There we go. So these scales both read 8 newtons for this problem. The string that's pulling to the left is an angle of 37.7 degrees. That looks like the angle measured from the vertical. I want the angle, well, I could work with that. The other angle over here then, let me do some quick mental math or just look down in the corner where it gives me the three angles. So this looks like 52.3 degrees. This is 37.7 degrees over here, okay? The other one then, this is the 35.7 degrees. So this is 54.3 degrees. If I'm making sense of that, I gotta think about how this looks in my arrow diagram. So if I was going to draw an arrow for this 8 Newton force, I think the way I'm looking at this, I think this is what I would traditionally call the angle between the string and the vertical, because here's the string and here's the vertical, right? Right? Okay. So I'm going to say that this is an angle of 37.7 degrees. Wow, I really don't like that. Can I change the color of my pen without having to redraw that? Let's find out here, friends. Can I just go here and go a color that we can see? Nope, that didn't work. All right. So anyway, so that's, I'm going to hedge my bets on that's 37.7. We'll find out here soon enough. Like the goal here in the end is to figure out the mystery mass, how much mass is hanging there. Okay. So then my other angle, or my other arrow, I should say, going off the other way, is also 8 newtons. You forgot to write 8 newtons, Mr. Harding. There we go. So 8 newtons over here, and this one's 8 newtons over here. And the angle's pretty close, right? 35.7 degrees. If I'm drawing this to scale, I'm just going to call this one 38. I'm going to call this one 36, but I'm going to use a different technique here. But you can kind of see, right? If I was going to draw this to scale, draw a YMCA or a rad, then there's a third arrow here. That third arrow is due to the weight of the hanging mass, right? So this is the FG of the hanging mass. So mass, mystery mass, MM, Earth. I want to know how much that is if I draw these arrows to scale and I keep their angles correct, right? If I have this angle with respect to the horizontal, and I bring it over here and I still measure it to the horizontal, boom, there we go, I'm done. But some of you kids like to do things the slow way and solve this out with math. So I thought I'd take a look at that approach quick, or not quick, as it were. So what I'm going to do here basically is take this thing that's at an angle and I'm going to turn it into a right triangle. Because, you know, the calculator mafia, the calculator Illuminati, want you to use your trig functions. So I've turned this into a right triangle by putting some dashed lines there and a little square. And now what I'm going to do is take one arrow and I'm going to turn it into two arrows. I'm going to figure out the two arrows that make up a right triangle that to give us this 8 Newton arrow. Okay. So this green arrow plus that red arrow is the same as that blue arrow. Okay. How I'm going to do that, a little trig. So we could do law sines, we could do SOHCAHTOA because it's a right triangle. I want to find the side that is opposite this 35.7. So that's so sine theta equals opposite over hypotenuse. Okay. I'm going to say the sine of 35.7 degrees equals the opposite side. I don't know what that is right now. Divided by the hypotenuse, which is 8 newtons. So 8 newtons times the sine of 35.7 degrees. Okay. Let me pause this ever so. Ooh, is the pause right there? Pause. Pause? I don't know that pause. Pause. All right. Yep. This does what I thought it did. So to get the opposite, I'm going to multiply both sides by 8, right? That gives me 8 sine 35.7 equals opposite. And then I can just pop over here into the handy-dandy little Desmos calculator. You get to that the same way you get to Desmos to graph. I just clicked on calculator. And I just take 8 times sine of 35.7. I'm in degree mode. That's kind of important. And it tells me 4.6683296910. Oh my gosh, all these numbers. Let's call that 4.7. All right, back over here. So that is how many newtons this red arrow is. Okay, 4.7 newtons pointing straight up like that. I'm going to do the same idea for the green arrow down here. This is adjacent to the 35.7 degrees. It's my adjacent side. That's K, my favorite trig function. I like it so much that I gave my son Charlie the initials K. It's Charles Allen Harding. All right, so cosine of theta, angle theta, equals adjacent over hypotenuse. So that's going to be cosine of 35.7 degrees, there we go, equals adjacent, I don't know what that is yet, divided by the 8 newtons. Multiply both sides by 8 newtons gives me 8 newtons times the cosine of 35.7 degrees. That will equal the adjacent side. Okay, and I can see it's probably a little bit longer than the red arrow because this angle up here is a little bit bigger, right? The bigger angle is going to open to the bigger side. This must be 54.3 degrees.
It is now time for A lunch. Students with B lunch should go to their fourth period class.
Thanks, Dr. Schultz. All right, so pop back over to the Desmos thing. 8 cosine 35.7. Change my trig function out. What do we got to do here? Boop, boop. Cos 35.7. Should be a little bit bigger. Yep, 6.5 basically is what I got there. All right, 6.5 newtons is that arrow. Okay, now I'm going to pause this so I can figure out the other one quick. I mean, it's basically the same process, right? You don't need to watch that again. Pause. All right, you missed a bunch of announcements. 8 cos 37.7, 6.4, 8 sine 37.7, 4.9er. Pop back over into the notebook. So I got those arrows. 6.4 is the horizontal part of that right triangle. 4.9 is the vertical part of the right triangle. Okay. This, again, what I'm working towards is a mathematical way of solving this out, but I'm going to show you diagrammatically that if I grabbed this arrow and this arrow, oh, I wish you were an arrow, and then I go with this arrow, what? And this arrow, yo, give me that arrow. Okay, and I draw my whatever arrow I need to complete this diagram, right? That's going to look like, oh, wow, that's poor. Sorry, the beeping scared me. All right. So that looks like that. Okay. Dig how if I took this arrow, this arrow. Go down. No. Okay. Took this arrow and, oh my goats, this arrow and add them together, I would get the same, I would need the same missing arrow here to fill that in. Okay, so whether I add the four components, these are called the four right triangle components together, or I just add the two original arrows together. Arrows have tips. Yeah. So, boop. So that should look like that, and that should look like that, and that should look like that. But you get the same thing. Okay, all I've done is make this more complex by involving math and using four arrows where I could have just used two arrows. Okay, mathematically then, now it matters that these arrows are pointing sort of different directions, right? This blue one is kind of up and to the right, and this yellow one is up and to the left. Okay. This is going to be real slow and painful. Sorry. Boop. And notice how it doesn't really matter which side I drag these red and green arrows to, because they were pretty much the same. Oop, you go over there because you've still got your arrow tip. Oh, yep. Process of elimination. You can see that this should be, oh, come on, man. There we go. This should be over here. And then this clicking on arrows thing works really well. Wow. There we go. Got you. Khan Academy is so much better with the diagrams. Shut up, self. All right. So there we are. Okay. So back to kind of where I started from. I've got one 6.5 Newton arrow that's pointing to the right, and then I've got this 6.4 Newton arrow that is pointing to the left. Okay, so mathematically, we would consider that to be positive 6.5, this to be negative 6.4. If I add those together, positive 6.5 plus negative 6.4, I'm going to get 0.1, but recognize that that's basically 0. Okay, that's why this yellow arrow isn't really pointing to the right or left, because the amount of force to the right, the amount of force to the left, pretty much taking care of each other. These red arrows are both positive. I've got 4.9 and 4.7. 4.9 is positive, plus positive 4.7 newtons. Mr. Harding, use units on your work, please. Yep, I'll do that. So what does that add up to? That's going to be 9.6 newtons, which you'll recognize is darn close to 10 newtons, which is good because that mystery mass, I should have done like a little reveal video, but you'll just have to trust me, is a kilogram. Okay. So that's how that shook out. So there was 10 newtons down due to the gravitational force, or whatever, however you want to think about it. That's the weight of that kilogram. And then these two forces, the 8 newtons going up and to the right and up and to the left, balance that out. All right, this video is getting longer than I like, so let me pause this real quick while I do the next part. Sorry for the arrow shenanigans. Oh, all right, so here's the math for those other arrows. Again, I'm just taking the amount of force of what is basically the hypotenuse, the actual tension in the string, and then I'm using cosine and sine to break that down into the x and y components. I'm turning my force that's at an angle into two arrows that are nice and resolve to the x and y axis. Okay, so what happens here? So I've got 11.2 to the right, I've got 10.8 to the left, I've got 2.2 up, I've got 6.5 up. So when I go to resolve these forces, I'm going to add the forces, excuse me, sorry. So I'm going to add the forces together in the y direction, the vertical. That's going to be 2.2 newtons plus 6.5 newtons. Mr. Harding, you should write that in red. The arrows in red. Shut up. All right, so that's going to work out to be 8.7 newtons, which is basically 10 newtons. Don't ask why. And again, so 10 newtons, what's up with that? That's because if I take these two arrows and add them together like that, poof, I'm going to end up with an arrow here pointing straight down, and that arrow would relate to the weight of the object that's hanging there. And that happens to be a kilogram. So this would be like FG, kilogram, comma, Earth, or something like that. Okay. That's what's shaken. And so this would be FT, kg, comma, scale 1. And this would be FT, kg, comma, scale 2, or something like that. Right? You get the idea. You add those arrows together, or you can add these 4 arrows together. If I add the X arrows together, I've got negative 10.8 newtons plus 11.2 newtons, and that equals, math, that's going to be about 0.4 newtons, which again, that's basically 0 newtons. Okay, so notice that these forces in the X direction take care of each other, and then the tension, I could call this FTY probably. Ft comma y, ft comma x. The forces in the y direction are balancing out the gravitational force that's going straight down. Okay, that's what's shaken here. Good luck with the mastering.